N factor. So here sulfuric acid releases 2 H plus ions, right? Okay, or sulfate ion will be also formed now. So what is the total positive charge you are seeing? 2 into plus 1. So it is plus 2, or minus 2 into 1. So it is minus 2. Either you take total positive charge or total negative charge. That is what its N factor. So normality will be 2 into molarity for sulfuric acid. Okay. We'll start the lesson here. Classification of elements and periodicity in properties. See, from this chapter, see, whether you know the previous chapter or not, that is not a matter here. So it is completely independent chapter now. Okay. So those who join late, please try to follow it from very beginning. Okay. Don't think we have missed the last class, so we cannot understand this. No, you can easily follow this, and it's a very simple and easy topic. From this chapter, you can expect 2 questions. Directly 1 question and indirectly maybe 1 question or more than that also. Okay. But this is a very basic topic, basic chapter to understand the other topics of chemistry. Okay. Right. So here, classification of elements. What does this line says? Classification of elements means, see, at the early stages, like scientists were doing some experiment and trying to find some elements like that. Okay. So at very early stage, it was only very less number of elements known, but as time goes on, the new elements were discovered and it's becoming a very big number of elements. Now remembering all the elements become difficult, and remembering all those elements and their properties is very difficult right now. So they thought, let us classify these elements based on some properties or whatever might be. Okay. So because different scientists taken different type of like classification. Okay. So now the first classification here we have, see, first of all, why do we require to classify them? See, when you go to a library, like it contains lot of books right now, but you will be entering the library and you will be directly going to that section where the book that you are looking for, you will go and take that book right now. So similar to that, when you are looking at the elements, if you wanted to know the if there is an elements like classified based on similar type of properties at one position, so you can directly go and you can read that particular generalized properties of that group elements or that period elements, and you will feel you got everything right now. So it is easy when you classify the elements, same like we are classifying or we are segregating books in our library. So this is what the basic way of understanding the classification of elements. Okay. So now what are the approaches? So who is the first person to develop this? Daubernier triad. See, triad means it's a set of 3 elements. So what he taken? So he taken 3 elements like A, B, C are the 3 elements he taken. Let us consider. Now he arranged these elements based on their atomic weights. So increasing atomic weights he arranged. Okay. Now when he arranged them, like taken 3 elements are arranged based on their increasing atomic weights. Okay, now he observed that the atomic weight of middle element is an average of atomic weight of first and third element. So what I can write, average, like atomic weight of middle element will be equals to average of A plus C by 2. Like this he got some identification. Okay, so now what are the triads he has taken there? See, these are the triads like lithium, sodium, potassium. Next calcium, strontium, barium. Here chlorine, bromine, iodine. Okay, so now it was seems like this whatever the triad classification is given, it is applicable for only few set of elements. Okay, now if you observe here, like for some elements it is observed to be exactly the average of the middle one, but for few elements it is very nearest to the middle element, not exactly the value of middle element. It means this whatever the triad classification is there now, it is not able to follow for all the elements that were known at that time. Only for few set of elements only it is applicable. Therefore it was having some limitation, then got failed. Okay, so now what is the drawback or limitation for Brownian triads? It could not arrange all the elements which are known at that time itself. It means it is only applicable for few set of elements. Okay, so these are some triads you can remember. Okay, next let's move forward. Next classification is what? Newland's law of octaves. See, law of octaves, it means 8. Okay, so what he did, he also arranged the known elements increasing order of their atomic weights. Now he found that for every first element and every 8th element having similarities in their properties. Okay, so it means like that musical note is there now, like so like that first sa again sa after the 7th one, the 8th one is again sa. So like that he have found that element first and 8th have similarities in their properties. See, lithium, if you count up to here, sodium having similar properties. Next beryllium, so 1 2 3 4 5 6 7 8. Beryllium, magnesium, like boron, aluminium. Like that every first and every 8th element are having similarities in properties. Okay, so now when this law is proposed, this Newland's law is given, so at that time what is this, noble gases were not discovered. What not discovered? Noble gases. So if you observe this Newland's law of octave at present situation, how it will be? Now noble gases are there. At that time noble gases were not there. So that's way for every first and 8th similarities were observed. Now what happens? Now noble gases are included in the table now. Now it becomes every first and 9th element. What it becomes? First and 9th element will be observed as per his classification. Similarities in properties. Okay. Now what are the drawbacks? This rule is applicable only up to calcium. Okay, and after that it fails in the case of heavier elements. Okay, therefore it is also got failed. It means for only few set of elements up to 20 elements only it is applicable. Okay, then later it got failed. So it is also not a exact one to classify the elements. Like this slowly developments are keep on going. See, in the previous case only few set of triads they have taken. Now there are some bunch of elements right now. So slowly developments are going on or not? Yeah. So even if you are also feeling you are very dumb or you are very dull, so you start working hard. Slowly you can also get improved as like they developed the periodic table. Now you see how beautiful the periodic table will be. Okay, so you can also think about your career after sometimes looks very beautiful if you work from now itself. Okay, right. Next, who is next here? Lothar Meyer. So you remember it as Lothar Meyer curve. So what he told is he taken some properties like atomic volume versus atomic mass. See, he presented the classification of elements in the form of a curve. Okay, between so what are the things he taken? Atomic volume, atomic mass, and stated that the elements that are having same properties are occupying same positions on that peaks. For example, if you observe, what are the alkali metals you know? First group elements in the periodic table. Hydrogen, lithium, like this now. So ignore hydrogen. Okay, now what are the elements we have? These elements. Now you observe that elements in this in this curve, where they are. See here, lithium. Where is sodium again? Here sodium. Okay, next potassium, sodium here, potassium here, next rubidium here. If you observe sodium, potassium, rubidium, all of them are alkali metals now. So they are at the peak of the graph right now. So it means those elements having similarities in properties occupying almost same position on the peaks of the curve. Is this clear? Okay. So in the same way, let us take some other elements. See, halogens, if you compare, like what are the halogens you know? Chlorine, fluorine, chlorine, bromine, iodine. So now if you observe, fluorine, see, it is in the increasing order of the curve. Okay, and here also, here see, and somewhere here bromine also, right now. So the increasing order of the curve, if you observe, there it is occupying the position right now. So is this clear? So those elements are having similarities in properties, occupy say almost similar position on the curve. Okay, now you just tell me, is it really easy to remember the positions of each element on the curve? No. It is very difficult right now. So that's why this is also got failed due to it's very difficult to remember all the positions of the elements right now. Okay, but the questions from this curve you can expect like this. What are the positions or where we can observe alkali metals and the Luther-Meyer curve? Like this we can expect. See, you can remember these direct statements. Alkali metals such as sodium, potassium, rubidium, which have similar properties, occurs at the peaks of the curve. When it comes to halogens, which have similar properties, occurs at the rising or ascending order of the ascending part of the curve. Ascending means small to big now. Like that only we have seen, like this they have seen here, one fluorine, chlorine, like that we have seen. Okay, right. The next one, noble gases such as neon, argon, krypton, which have similarities in properties, occurs just before the so noble gases, right? So noble gases means here you can see what we are discussing about noble gases, and noble gases such as occurs before, just before alkali metal. See, if this is alkali metal, just before alkali metal we have argon. Okay, if this is rubidium, here we have krypton. Just before alkali metals we are seeing. Okay, you just need to remember these lines. Okay, and here you can see hydrogen and helium are seems to be exceptions for this rule. Okay, so these are the points to be remembered here. Next, who is next? So Mendeleev given some proper structure to the almost some clear explanation, some kind of structure to the periodic table. He shaped the periodic table, we can say. Later on, the modern periodic table we have, so it is almost done with it. Okay, and here you can see what he told. Mendeleev arranged elements in the horizontal rows and vertical columns of a table in the increasing order of their atomic weights. So what is the primary property they have taken? He has taken atomic weight. So the physical and chemical properties of elements are periodic functions of their atomic masses. Okay, so he considered atomic mass as the fundamental unit. Based on that, he classified he arranged the elements in the period in a table. Okay, so how many tables he how many rows he has taken, we'll see all those things. Okay, so it is based on what? Atomic weight. Okay, so when he is classifying, how many elements were known? 63 elements were known. So at that time noble gases were not discovered. Then next here, he was the first scientist to classify the elements in a systematic manner. That is what horizontal rows, vertical columns we are saying now. Okay, so now horizontal rows are called periods. What is that? Periods. So how many are there? 7 periods. The next vertical columns are called, see, horizontal rows. Like this, how many are there? 7. Like this, how many are there? 8. So you just remember here up to 8 only. Okay, as per him, he told that there are 8 groups. See, vertical columns are called groups. How many are there? 8 groups are there. In which periodic table it is? Mendeleev's periodic table. Okay, now if someone asks you now, you should say it as 18. What you should say? 18 groups. Okay, now this 8 is there now. How many he told? 8 he told. So he classified this. Okay, next 8 ఉంది కదా. So 8 groups I am saying now. So in these 8 up to 7 groups, what I am saying, up to 7, they have again subdivided as 1A, 2A, like 1A, 1B, 2A, 2B, like that up to 7 they have classified. The 8th one being as like that only. It is not classified. Only 7. Okay, like that. So each group up to 7 is subdivided into A and B subgroups. Okay, so A subgroups and B subgroups, like that they have divided. So now these A groups are there now, like 1A, 2A, 3A, 4A, like that are there now. So those are called normal elements. But 1B, 2B, where you will be seeing this 1B, 2B, 3B, like these things, like transition elements are there now, there you will be seeing even now in the periodic table. So these B groups, subgroups, elements are called what? Transition elements. Okay, now I will show you the periodic table later. Just follow these lines. Now the 8th group consists of 9 elements. What they contains? 9 elements. So 9 elements means which elements are exactly means? This 8th group means, you tell me, ferrous, cobalt, nickel. So now here down elements are there now. See, these elements we know. So these are like whatever here comes, like scandium, titanium, vanadium, chromium, manganese. Here we have like this manganese. After this again we have copper, zinc, like this. See, copper family will be considered as 2B. 1B. Zinc family as 2B. Next come here to directly to the scandium. So why it is 1B, 2B, I will tell you. Just follow me. See, scandium, it should be 3B. Titanium, 4B. Like that, here if you come up to manganese, it becomes 7B. Okay, this all these 3 elements are there now. Which one? Which one that is? Ferrous, cobalt, nickel. All together is considered to be 8th group. Now, how many elements they are saying? 9 elements. Like after this we have ruthenium. These elements are there, osmium. Again here also we have. Here also we have. So all that 9 elements. They are saying about this 8th group. Okay, is this clear? Okay. Okay. Next, what he is saying, elements belong to same group exhibits similar properties. Okay. So now what are the merits or advantages of Mendeleev periodic table? See, he is told that this is the first time like all known elements were classified into groups and periods. Okay. The next, we can he also predicted some unknown elements, like in future we may going to discover few more elements, so let us leave some space for them. Like that he left some space in his periodic table. So what he named them? See, for gallium, at that time gallium was not discovered, so he just mentioned it as Ica aluminium. So for scandium he told Ica boron. For silicon he told it as for germanium he told us Ica silicon. For technetium he told it as Ica manganese. Now in the exam, what type of questions you can expect till now from our discussion? Either about these 4 names, boron, Ica boron, Ica silicon, Ica manganese. Okay, one more thing I missed. Ica aluminium. So you just remember this. See, gallium, aluminium, gallium, like that similar sound you are hearing now. Gallium, aluminium, like that. Okay. Then next, silicon, germanium belongs to same group, like carbon, silicon, germanium. Okay. Silicon, germanium. Manganese and technetium also belongs to same group. Below manganese you have, you can remember like that. Okay, so now from this you can expect, or that lines I told now, what lines? Luther-Meyer curve lines are there now, from there also you can expect, or otherwise the triads are there now, from the triads also you can expect. So what are the three triads you have seen? Chlorine, chlorine, bromine, iodine. Next one, lithium, sodium. Next one, calcium, strontium, barium. Okay, now what are the demerits of Mendeleev classification? See, what is the fundamental unit he considered? Atomic mass. See, if we consider atomic mass, it means first lower atomic weights, next higher atomic weights, like that it should be in the increasing order of atomic weights, yes or no? But there were some elements where the higher atomic weight is coming first and lower atomic weight coming second. So is this proper way of classification? No, this is demerit only, no? He is not unable to explain the reason behind this. Okay, so what are those elements? See, that whatever the scenario we discussed, that is called anomalous pairs of elements. So there are some set of elements having this kind of phenomena. So what are those here? Argon and potassium. See, potassium is 39.1, here argon is 39.9. It means who should come first? First potassium, then next argon. But in the real periodic table it is argon first, next potassium. Is this correct? With his explanation it is not correct. So this is considered to be one anomalous pair. Okay, what is that? Anomalous pair. Similarly, cobalt and nickel. What is that? Cobalt and nickel. So remember these pairs, anomalous pairs. Okay. Not only this, what is the basic fundamental thing he considered? Atomic weight. It means if different atomic weights, difference in the position, there should be different positions should be allocated. Now see, for carbon, how many isotopes are possible? C12 you are writing, C13 you are writing, C14 you are writing. See, atomic weight here it is 12, 13, 14. It means these three isotopes should have separate space now, separate position in the periodic table, but he given only one single position. Is it correct way of justification? No. So it means this is also a drawback now. There is no explanation. Okay, because all elements were placed at as just a carbon atom in the table. But he is saying I have arranged based on atomic weight. Will you agree with this? No. So we can consider this is also as a drawback. Okay. So now position of isotopes you got, anomalous pairs you got. Next one is position of hydrogen. See, hydrogen resembles with both alkali metals and halogens. See, alkali metals like lithium, you know now, atomic number 3. What is the electronic configuration you are writing? 2s1. Now tell me for fluorine. 1s2, 2. See, they are saying a line, hydrogen resembles with both alkali metals, halogens. Now tell me for hydrogen, what is the electronic configuration? See, similar to this alkali group elements, it also has 1s1, like it is 2s1, 3s1. If you go down, it is also having like 1s1 electronic configuration only, right now. So it means it may show some resemblance with first A group elements like alkali metals. Okay. Now if you observe, fluorine is a 9th element now. After fluorine, who is there? 10th element is neon, noble gas now. So after hydrogen also, who is there? Helium. That is also noble gas. It means like halogens, hydrogen also shows some properties. It means this fellow is having some properties, resemblance with alkali metals as well as halogens. That's why the position of hydrogen is not yet fixed. Even now also there is no fixed position for hydrogen. But just for writing purpose, mostly you will be seeing it with the first group elements. But in proper way you should write somewhere here in the middle. Okay, because its position is not exactly mentioned. Okay, is this clear? Next, modern periodic law. So who given this? Henry Moseley. So what he considered is, he did see, he taken the element, okay, some metals or some like sheet like species he taken, and he incident this with a cathode ray tube. What rays he used? Cathode rays. So when these fall on that, some energy will be emitted out now, so that like some radiations will comes out now, so that radiation will have some frequency. Okay, so by observing that, see here in 1903 English physicist Henry Moseley observed regularities in the characteristic X-ray spectra of elements. So what he did, he plot a nu, that is what, frequency versus atomic number. Okay, now he got something like this, he has observed. Okay, so symmetrical increment he observed. Okay, so now what he told is, yeah, so based on this observation I can say the fundamental thing we need to consider here is atomic number, not atomic mass. So the next what he told, the modern periodic law, the physical and chemical properties of elements are periodic functions of their atomic numbers. Okay, previously it is considered to be atomic weight, now it is considered to be atomic. Now as per this modern periodic table, how many groups we have? 18 vertical columns called groups. Next, so from 1 to 8 plus 0 for inert gases. See, we have some IUPAC like organization is there now. So as per them, see, this is what the modern periodic table we have. So when I say IUPAC like standard way of numbering them, so you start numbering 1 here, go like 1, 2, 3, 4, 5, 6, 7 like that up to 18. Okay, that's why we are saying 18 groups. Now when it comes to Mendeleev classification or normal classification, it is what? Like they have considered 1 to 8, okay, 1 to 8 and 0. So 0 is nothing but this noble gases. Okay, now what I told you, from this 1 to 8 take 1 to 7 and they subdivide them into A, B. Like this is 1A, this is 2A, this is 3A, 4A, 5A, 6A, 7A. Up to here it is 7A. Is this clear up to here? Now when it comes to B classification, 1A is over, 1B should be there now. That 1B comes here with a copper. This is 2B. Next 3B, 4B, 5B, 6B. Next 7B, like 7B. Next what I told you, all these 3 set elements are 8th. Is this clear? Okay. Now if you observe what is the electronic configuration of this generalized like this first group, NS1. Okay, that's why you can say it as 1s1, I mean first A group. Okay, here what about copper family here? What you will be writing? It is like 3D10, 4s1. Again this is also S1 now, so you can consider it as 1. Here it is 4s2, 2B you can remember. This one like 3D1, 4s2. So total how much? Sum 3. Like that you can remember. Okay, is this clear? Okay. Next. Next one is what? Position of isotopes. See, previously there is a controversy with the position of isotopes, but here there is no controversy. Why? Because all isotopes have same number of protons. So based on protons only now we are saying atomic number. So all isotopes can be placed at the one position because all of them have same number of protons. So the controversy with respect to the isotopes got resolved. Okay, now it is accepted. Okay, next one. Here also that anomalous pair we have seen now, like argon, potassium, cobalt, nickel and tellurium and iodine. So now previously it is atomic mass, but now it is number of protons. Okay, number of protons are properly arranged. I mean based on atomic number means we got rectified with this anomalous pair also. So you just remember these two here. Next, here we have lanthanides. Again remember all F block elements lies in which group? They will ask you. 3B. Already in the basic classes I discussed in 3B group all these F block elements will lies. It means in 3B only we have lanthanides and actinides. Okay, next. In modern periodic table, a diagonal line separates out metals, metalloids, non-metals. I will show you that. So in this modern periodic table, if you go from left to right, what happens? Metallic nature decreases. Here completely S block elements means completely metals. Next D block elements also metals. Okay, when we go to the what? P block, there is a line separating metals and non-metals. In between we have a okay, are you trying to imagine that? Okay, next. Elements which are from same group have same same general electronic configuration. So now what are the demerits it has? Position of hydrogen is still controversial. Next, because just now we discussed. Next, if you see all noble gases having like 8 valency electrons, but helium only 2. So this is also one of the drawback. Helium is inert gas but has different electronic configuration compared with the other inert gas configuration. And lanthanide actinide positions is separated, not in the main block, main periodic table, main frame. Okay, that's it. So are you ready to write the periodic table once again? That 2 times we have written previously, right? Are you there? Like most of you are there. Okay, so today also we'll write once again. Yes, tell me. Okay, hydrogen, helium. Okay. Next. Boron. Next. Okay, next. Yes, tell me. Okay. Okay, finish this. Lithium, sodium, potassium. This one. Beryllium. You can remember LENAC. Lithium, sodium, potassium, rubidium, cesium, francium. Next one, this one BMC, SBr. What I am saying? BMC, SBr means strontium, barium, radium. Okay, next, come this side. We'll finish this. Okay, this one, boron, aluminium, bag, gallium, gallium, indium, thallium, nihonium. Next, this one, carbon, silicon, germanium, tin, flerovium, Fl. Next, this one, arsenic, next, Mosconium, Mc. Next, oxygen, sulfur, selenium, tellurium, polonium, livermorium, Lv. Next, this one, fluorine, chlorine, bromine, iodine, astatine, tennessine, T. Next, this one, krypton, xenon, oganesson. Next, this one, yttrium, zirconium, niobium, molybdenum, technetium, next, this one, lanthanum, hafnium, osmium, platinum, aurum, this one, Rutherfordium. What I told you, this line, RDS, BHM, DRC. Tell me. Dubnium, seaborgium, borium, hussium, meitnerium, darmstadium, roentgenum, copernicium. Okay, so now look at this. Wait, this one is like how many periods you are seeing? First, second, third, fourth, fifth, sixth, 7 periods. Okay, so now D block elements starts from which period? Fourth period, just fourth period. Okay, in fourth period you have 3D series. Which series? 3D. This is 3D series, this is 4D series, 5D, 6D. So there are 7 periods. In fourth period we have 3D series, fifth period 4D series, sixth period 5D, seventh. Okay, remember that. Next one. So from which, what is the atomic number here? Starts from scandium 21, ends with 30. Here it starts from this one is 39, goes up to 48. Okay, sorry, 48. Next, so this one 50, 57. This one is 72 to 80. 72 to 80. Okay, just you need to remember these numbers, very important, these numbers. Next, this one. So it starts, this is 89 actinides. After that, 104 to 112. Okay, so now they will ask you, once again, just make it a separate note. 3D series from where to where? 21 to 30. So 21 is what? Scandium. 30 is zinc. Next 4D series is yttrium. 39 to cadmium. 48. Please try to make one separate note of it. Okay, next this one 5D series. Lanthanum is there. Lanthanum 57. After this 72. From what is it? Hafnium 2 mercury 80. Next 6d series, you tell me fast. Actinide, what is the atomic number? 89, comma, starts from next. Rutherfordium starts from 104 and ends at 112. What is that? Copper necium 1112. Okay, make it note of this. Okay, right. Next, what are the elements we have? F block, we haven't written F block now, so let's try it once. So F block starts from where? F block elements. So these are lanthanides. Lanthanides, where it is? Which period it is, ma? Lanthanides, 6th period. Okay, what are these lanthanides? Lanthanum, cerium, praseodymium, neodymium, promethium, samarium. Ma, please listen here. If you know the electronic configuration and elements of 5 like a D block and S block, you have 2 marks in your hands if it is for EAPCET and 2 questions if it is for NEET. Okay, it is just based on their elements, atomic number and their electronic configuration, that's it. Okay, now follow me here. So cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, Tb, okay, erbium, dysprosium, okay, holmium, erbium, thulium, ytterbium, lutetium. Okay, see, either you remember this. So will you, like, you know already these elements? Okay, so you know at least a little bit Hindi? Yes. I will try to make one line, but it's completely up to you to remember. Okay, see, I will tell you one simple trick. What elements we are studying about? So there is a girl, her name is Lasina. So she is very pretty. Okay, so Lasina is pretty and she has 2 friends. Okay, one person name is Pramod and another person name is Samir. Okay, Samir. So they want to go to Europe. So Europe, Gadi, gadolinium na. So for going Europe, they required vehicle na, Gadi. May ticket देखकर लिया, तुम भी ले लो. Okay. Lasina, see here. Lasina means what is this? Lanthanides. C. Cerium, pretty. Praseodymium and neodymium. Next, see, pretty means PR na. After again, see the most confusion thing is whether samarium comes first or promethium. So PNP, remember like this. First P, after N, again P. Okay. So what I am saying, Pretty and Pramod. Again one more friend is Samir. So Pramod, Samir. So they where they wanted to go? Europe. For that they required gadolinium. Next ticket means terbium. Okay, terbium is over here. Okay, Deker. It means they found the ticket. Okay, so dysprosium. Okay, so here H is there now. Holmium. Okay, next E again. ER is there. Erbium. Okay, thulium. Okay, so it is ytterbium, lutetium. Just remember like that. Okay, so either you remember this line directly, these elements directly, or if you are at least little bit familiar with Hindi words, it is easy to remember these lines. Okay, so what is that line? Otherwise you can make your own mnemonic and remember. Okay, that's it. So from where to where these elements, number from where to where? 58. 58 to? So 58, 9, 60, 61, 62, 63, 4, 7, 8, 9, 7. See, why I am giving this one is, you read this, for next 2 days, you will feel like you remembered. If I ask you, you will remember the names, but not in order. So that time, this mnemonic may help. Because it is something like, it connecting words are there now, it has some connecting words. So from that, at least you got that proper order. Okay, so that's it. Next one is what? Actinides. Okay, let's try this actinides also. Actinides belongs to 7th period. Actinides. MD. Okay. Okay. So how can you remember? From where to where actinides are? 90 to 103. So here also I will tell you one simple way. It's your wish to follow. See, there is a like, you know Lawrence master? Lawrence, who is this? LR. Lawrence. Okay. So Lawrence is very good in acting. What will say? Arey, you are a top actor. Re. Will say like that or not? Okay. Acting top. Okay. Arey, it's your wish to remember or not. Just I am giving as my duty. So first start from here, then come here. Read it once or twice, you will get everything. ఏమైందమ్మా? అరే ఇది అంతా మీ ఇష్టం రా, మొత్తానికి మాత్రం అవి రావాలి. Okay, done. So what are the elements? Tell me once again. Thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium. Okay, remember this. So if you see in your what is that, NCERT book or something like that, it will be mentioned as UUH, something like that. So what is this UUH and all these things? See, when like previously few years back, like only few set of elements were known now. So after 100, elements were not known at that time. After 100, atomic number 100, elements were not known. But after a few days it got prepared, whether synthetically or naturally, whatever it might be. So now at that time, so if the element atomic number is greater than 100, what I am saying, if element atomic number is greater than 100, so IUPAC standardized some rules. Okay, so he told if it is 1, you should call it as un. If it is 0, you should call it as nil. If it is 2, you should call it as bi. If it is 3, you should call it as tri. Like this, they have given. Let me check. Let me show you this. Okay. If it is 1, what you should say? Un. Okay. Let me show. 0 nil, 1 un, 2 bi, 3 tri, 4 quad, 5 pent, 6 hex, 7 sept, 8 oct. So now last element, what is that? 103, lawrencium. So lawrencium IUPAC name? Un, nil, tri. You should write these things and end the name by adding IUM. Un, nil, trium. Okay. Now before lawrencium, what we have? Nobelium. Before nobelium, mendelevium. So mendelevium, MD, what is the atomic number? Now tell me. Un, nil, anium. Un, nil, anium. Okay, like that. Okay, if it is 100, un, nil, ium. Okay, next. If it is 126, okay, un, bi, hex, ium. Okay, done with this. Okay, look at these ones. Mendelevium, just now we discussed what is its atomic number? 101. So it should call as un, nil, anium. Next nobelium 102, un, nil, bium. Next lawrencium 103, un, nil, trium. Rutherfordium 104, 105, dubnium, un, nil. Next seaborgium. Next borium. Next hassium 108. Okay, so like that, if you see there is a question here we have in the exam, so just try to match this. First one, mendelevium atomic number how much? 101. Lawrencium, just try to match them. Where do we have? Correctly. Incorrect one they are asking. Identify incorrect one. This one? Why D? See, what is this? This is triple one. Triple one here is Roent genome, or we can say, but they mention it as Dung stadium. Dung stadium is, so that is the only incorrect one, remaining all are correct only. See, Mendelevium 101, you just take Laurentium 103 and the Seaborgium 106. So this is 106 only now, Unnil Hexium. Okay, so it is purely based on that IUPAC nomenclature greater than 100. So you can give based on that. Next. So how can we predict like which block an element is belongs to, or which group or which period? How can we identify? For example, I am saying atomic number 17 belongs to which period, which group? I am asking. Okay, so element 17 means what is that? Chlorine. So chlorine now, so halogen belongs to which group? We can say 17th group, and which period they are asking? Third period. So now how can we give this? See, write its electronic configuration exactly. Like 1s2, 2s2, 2p6, next 3s2, 3p5. So this is 10 plus 5 plus 2, 7, 17. This is 10 plus 7, 17 is over. So element atomic number is 17 right now. So what is the last, the last electron entering into the which subshell? P. So it is P block element. Which block element? P block. What is this last n value here? 3. So this is called a principal quantum number. So by looking at the last highest principal quantum number, we can say which period it is particularly. Okay, so it is a chlorine is a third period element. Now how many valency electrons are there? 7. So for P block element, for any P block elements, you just make 10 plus number of valency electrons. How many valency electrons are there here? 7. So 10 plus 7. So chlorine belongs to 17th group. Okay, so what are the things I told you for identifying period? What to say? Its principal quantum number, highest principal quantum number. In order to identify which block, the last electrons entering into the which orbital, which subshell. Next, identifying group. If it is P block, add total number of valency electrons to the 10. 10 plus total number of valency electrons. If it is P block, we get to know now whether it is P block or not. If it is entering, last electron entering into the P block, we can say it's a P block element. So now what to do? 10 plus that number of valency electrons. Okay. If it is S block element, you just take whatever the number of electrons you are seeing in the shell. For example, I am saying 4s1, an element has electronic configuration as 4s1. So now tell me which group it is? See, only one electron is there now, so you don't take any 10, 6, 7 like that. Whatever electrons you are seeing, that group it is. Okay, for which one? If it is S block element. Now what is the highest number you are seeing here? 4. So it means it's a fourth period, first group, belongs to S block. Okay, is this clear? Okay, so now you got for S block element, you got for P block. So in between we have D block. So now D block elements, see what they are saying, number for D block now. So in number of ns electrons and n minus 1 d electrons again. See what is the general electronic configuration we need to write for S block elements. How many S block elements are like groups are there? One first group and second group. So for this it is ns1. For second group it is ns2. Next P block elements we have from 13th to 18th. Okay, so for them if it is 13th group, the general electronic configuration is ns2. ns2 is fixed. Now it varies from np 1 to 6. See, if it n like p orbital contains only one electron. Now tell me, this is 2 plus 1, 3. So 10 plus 3, which group? 13th. If p orbital contains 2, 2 plus 2, 14, 14th group element. If contains 3, 15th group. Contains 4, like tell me, like NS2, NP4, which group is this? Which family, like which elements are lies here? It's an oxygen family, oxygen, sulfur, selenium, like that. Okay. Now like this you can get a general electronic configuration for p block as NS2, NP6, NP1 to 6. Okay. When it comes to d block elements, like 3d series, 4d series, like that we have now. So for d block, what is the general electronic configuration you can say? See, n minus 1, d 1 to 10, ns 1 0 to 2, 0 to 2. Next, for f block elements, what is the general electronic configuration? N minus 2, f 1 to 14, n minus 1, d 0 to 1, ns 2. This is for lanthanides. This is for what? Lanthanides. If they particularly mention for actinides, you can write it like this: ns f 0 to 14, n minus 1, 0 to 2, ns 2. This is for actinides. Actinides. Okay. So if they only just mention f block element general electronic configuration, you can write like this. Okay. If they particularly ask for actinides, you should mention like this. Okay. That's it. So write this general electronic configuration. Now after this, I am giving you one element here. Tell me, like manganese I am writing. What is its atomic number? So how do you write this? See 25 now. I will tell one simple tricky way here. So 25, right? So 3d series element it is. So it is 3d 4s. Okay. S orbital you write this first number 2. D orbital you write second number. That's it. This is the general electronic configuration for manganese. So tell me for iron, 26. Tell me. 3d6, 4s2, like that you can write. Okay. Now next nickel, 28. Tell me. Like this. Okay. Now if I ask what is the group number of this iron, add number of d orbital electrons and s orbital electrons. How much? So iron is 8th group. Next manganese is 7th group. Nickel is 10th group, like that. So here we have generalized the formula for d block as number of ns electrons plus number of n minus 1d electrons. For which one it is? D block. Okay. So remember. Now I will tell you once again 3d series electronic configuration. Try to remember now itself. See, scandium atomic number is? So you should write it as argon. Argon is noble gas. 18 is over. Okay. These inner electrons won't participate in reaction. So now after 18 what we have? 3 electrons are required now, that is 3d 4s. So s will be 2, d will be 1. Next scandium, titanium. Tell me. This is fixed. 3d 2 4s. These numbers only you are writing. Okay. Next scandium, titanium, vanadium, 23. So tell me. Argon 3d3 4s. Next chromium, scandium, titanium, vanadium, chromium, 24. Tell me. 3d. Let us write as 3d4 4s 1 first. So how much? 4s 2. Okay. If you write like this, wait. So s orbital means one box you will be writing. S subshell means one orbital, one box you are writing. P subshell means you are writing 3 orbitals like this. Okay. D orbitals will be 5. How many? 5. In D subshell there are 5 boxes. 5 d orbitals will be there. So if this orbital contain either one electron in one like all these orbitals, that is called half filled. Either if all this, see, one box means one orbital. In one box, how many electrons we can fill? 2 electrons. Either they should contain, like they should be either empty, all should be either empty, or they should contain half filled, equally filled, it means half filled, or they should be fully filled. That can be considered to be stable electronic configuration. So now if I say this is 1s1, it is like one electron is there. So p orbital half filled means how it should be? Like this. Right now 3 electrons should be there, so 3p3, or one more stability factor you tell me, either it should be full filled, it means it should have 3p6, so with opposite spin. Now when it comes to D, how many boxes are there? 5. So either it should have D5 electronic configuration or D10. Okay, so now if you observe, chromium is 24. If I write 3d4 4s2, here if I give one more electron to d orbital, it becomes half filled. So that's why the electronic configuration changes from 3d4 4s2 3, instead of writing like this, I can write 3d5 5s. Just I am exchanging electron from s to d. So now chromium valence electronic configuration. So remember in that way. Okay. In the same way, if you keep on going, like there is no exception next. Next what? Who is that? Chromium. Manganese is there. 25. How you will write? Argon. What is this number? 5. So 3d 5. 4s 2. Like that you keep on writing up to copper. Copper means what is that atomic number? Copper is 29. So here after argon you will be having 3d 4s. See what is the trick I told you? These numbers. In S you put this number 2. D if you put 9. See how many electrons we can fill maximum in D? 10. Here 9 are there. Again if I take one from here and put here 10. So that's why it is becoming 3d10 4s 1. You can remember like this. So X found where and where? Copper. Here it is for half filled, here it is for remember like this. Okay. So now here what is the group number of copper if I ask? 10 plus 1 11. Next who is next? Zinc 30. Okay, like that. Okay, this is about this identification of things in the periodic table. Now periodic properties. What is that? Periodic properties. Now the elements have some properties now, like their size, their chemical reactivity, how they are accepting the electron or how they are releasing the electron. All this comes under properties. Okay, the first property here is atomic size or atomic radius. Okay, so atomic radius means what? If this is an atom, the center part is called nucleus. Okay, so from the nucleus, see, we know elements, like tell me some 1 or 2 elements, like carbon. What is the electronic configuration you are writing? 1s2, 2s2, 2p, 2 you are writing. Okay, now tell me one more element. If I write silicon, what you will be writing? Fast. Like 1s2, 2s2, 2p6, 3s2, 3p, 2 you are writing. See, if you observe, here I have written 2, here I have written 3. So it means, see, if this is the nucleus, around I am writing this like circles if you see this one. So these are called orbits. What is that? Orbits. This is n equals to 1, n equals to 2, n equals to 3. If I keep on going like that, the distance from nucleus to this valency shell, this is called shells, these numbers. So shells, increasing or not? Yes. So now as we go down the group, I mean, see, carbon, silicon belongs to the same group. See, it is 2s, it is 2p, it is 3p. So here it is up to here only we have distance in the carbon atom. But if I go from like silicon from here to here, so who is having more size, more radius? Silicon. So down the group, what happens to atomic radius? Increases. Okay. So now define the atomic radius means it is a distance from the nucleus to outermost shell of the atom of an element. Okay, this is called atomic radius. Now atomic radius will be measured in different ways. For example, we have some elements like metals we have in the periodic table, some are non-metals we have, some are metalloids we have right now. So different elements we have. So now when it comes to metals, we need to measure their radius in terms of their metallic radius. What is that? So what is this metallic radius, sir? Means, see, let us say this is a metal. If I press this, it is compressing? It is very rigid, na? So you have two metallic atoms. If you place them side to side, will they compress each other? No, they will be like this, very rigid, right now. So if this is a nucleus of one metal atom, this is another nucleus. So this distance, this is the radius of one atom, this is the radius of another atom. Okay, so if this is a distance d, so metallic radius can be given as d by 2. Is this clear? Okay. Now when I say covalent radius, what is the next point I am saying? So covalent radius means we know covalent bond is formed by mutual sharing of electrons. So for example, if this is an atom, it has one valency electrons. If this is one more atom having one more valency electrons in it. So now what they will do? They will overlap to some extent. So it means you are going to see there is some overlapping like this. See, previously it is very rigid. In which case it is? Metallic. Now what I am saying? Covalent. See, when it comes to covalent radius, some merging you have seen right now. So now here if I say this is a distance, now if I take half of it, it becomes covalent radius. So here the measuring, whatever we are measuring here, that is what? R covalent. Here it is what? R metallic. Okay. Now when it comes to one more term, van der Waals radius. What is that? Van der Waals radius. It means, see, this is a atom or a molecule you take. Let us say this is a atom or molecule you take. Okay. This is one molecule. One more independent molecule is there here. Like this. They are existing independent or not? Okay. So now if I measure the radius from here to here, this is called van der Waals radius. It means there is noble gases we have right now. Will they react? No. One noble gas exists here, one noble gas exists here. They might be having slight interactions, but they won't come closer to each other right now. So the distance between those two are considered to be diameter and half of it radius. But what radius? Van der Waals radius. So in noble gases case, which radius we are taking? Now tell me, in these three radius, which is more? Van der Waals. So that's why I am saying van der Waals radius is greater than metallic. See, between metallic and covalent, who is more? Metallic radius will be more right now. So metallic and least is for covalent. Like this you can take. Okay. So you can take this order like radius of van der Waals greater than metallic greater than covalent. Okay. Next. So now how it will varies? So van der Waals radius is large. The next? Metallic. Least is? Covalent. Okay. Now let us take this variation in the periodic table. How it varies in periodic table? So if you take periods means from where to where we are going? Like these are called what? Left to right. That is what periods we are saying. So if you take lithium, what is the second period elements? Like this you are writing. But if you write their atomic number, this is 3, 4, 5, 6, 7, 8, 9. But if you write their electronic configuration, how you will be writing? This is 2s1. This is 2s. This is 2s. 2s2. 2p1. This is 2s2. 2p2. Now if you keep on writing like that, so what you are seeing, atomic number is increasing or not? Atomic number is increasing means number of protons? Number of protons increasing means positive charges. This is the atom. Here we have nucleus. So atomic number is increasing means positive charge is increasing or not? If positive charge is increasing, what it will do? It will attract the electrons more towards itself. Now what happens to size? So now see here, atomic number is increasing means protons increasing, but that newly added electron going into the same energy level, same shell, like this shell only they are entering, they are not going to the upside, they are only here only. So now what it will do, the nuclear forces will drag this. So now what happens to its size? So across the period, atomic radius. So you can see the experimental data also. So lithium is 152, as we move up from here to here, fluorine is 64. Is it decreasing or not? Yes. So now no need of remembering the values, you just need to know the order. Okay, so here which is greater? Lithium, beryllium, boron, carbon, fluorine. See, if you observe, I have missed neon here, noble gas. Why I missed this? Why I have skipped that? Because it has van der Waals radius. So van der Waals radius is exceptionally greater than covalent radius and metallic radius. That's why we are not comparing. So in respective periods, noble gases will be having highest size. Okay, can remember this. Even third period elements you can see, sodium, magnesium, aluminium, like this we have. So which is highest one here? Size. Sodium. And least one is? Okay, remember this one. Okay, next. When it comes to group, so down the group what happens now? See, you are saying this is 2s1, this is 3s1, this is 4s1. So n value you are increasing now. That shell number is increasing means newly added electron going to the higher energy levels, which means away from the nucleus. If away from the nucleus means distance, so that's why down the group what happens to the size? Increases. Okay, whether it can be anything, like you can take this what is this, alkali metals, halogens. This is what the general trend you will observe. Okay, that's it. Next, ionic radius. See, if I say A is an atom, okay, so its anion means what I should write? Anion, A minus. Cation means A plus. See, what I told you, if more is a positive charge, what happens to their size? Size decreases. Why size decreases? More positive charge means it will attract the electrons more closely. So if electrons are attracted more closely, the size decreases. So that's why cation always have size lesser than its atom. Atom has size lesser than anion. Why? Anion means electrons are more now, so that electron cloud will be expanded. So anionic size will be increases. That's why you just remember this. Okay. Now same, whatever the variation we have studied for atomic radius, ionic radius also follows the same trend. It means lithium plus I am writing, sodium plus I am writing. Which is larger size? Sodium. So because both same group elements now, down the group what happens to size? Decreases. So like this. Okay. Next, isoelectronic species. It means what? Same number of electrons. So from here mostly question comes from this. I don't know why, but it is very easy to remember. Isoelectronic species means what? Same number of electrons should be there. Okay, so same number of electrons means, for example, I am writing here sodium plus sodium atomic number 11. So if I remove one, 10. Magnesium atomic number 12. If I remove 2, 10. Fluorine atomic number 9. If I add 1, 10. Oxygen atomic number 8. If I add 2, 10. Like that you can make isoelectronic species. Okay, all of them have same number of electrons. But nuclear charge is more at which case? Nuclear charge means positive or negative? Nuclear charge. Nuclear charge. Nucleus means this one now. If more positive charge, more is the nuclear charge you should say. So where do we have more nuclear charge? So here more positive charge or more nuclear charge strongly attract the electrons and size becomes small. If more is a negative charge, that electrons cloud expanded, size will be large. So now for an isoelectronic species, how the size variation? Cations will be smaller. Next, then anion. So more is the negative charge, greater is the size, like this. So I am making one simple relation. More is a nuclear charge inversely proportional to size, or size is inversely proportional to nuclear charge. Can we relate it like this? Yeah. Based on this, you can solve maximum number of questions. Okay, is this clear, everyone? See, more positive charge, it means more is the, if more nuclear charge is there, that will attract the electrons. So size becomes small, means it should be the least. Now here more positive charge is there, so its size should be small, and here it is large because it is an anion. More electrons are there. Okay, next. Try to get answer for this fast. Correct decreasing order of atomic radii. So tell me whether they are group elements or period elements. Period elements, from left to right, what happens to the size? So who is bigger here? Lithium bigger than beryllium. We discussed where it is. That's it. This one you tell me. Which of the following options represent the correct ionic radii? So what are the ions they mentioned? N-3, O-2, F-1. So now tell me, these are some random values they have given. Okay, so tell me which is larger size? So which is more negative charge? So it means it should have a bigger size. So bigger size means bigger value. Where we have? Where we have bigger value? So here and here. Then next this should be the second biggest value. So which one? So 1.40. So least one will be for this one. So what is your answer? That's it. Next. Next one is ionization energy. Okay, before that you tell me this one. Which are the following are isoelectronic species? Isoelectronic means what? All of them? Yes. Okay. Next, we'll solve few more questions. Next one is ionization energy. So what do we mean by ionization energy? See, if there is an atom A, what I am saying, atom A. Atom can be in any metallic form, like solid form, liquid form, gaseous form. First you convert that into gaseous state. What you need to do? So it should be in this form. Okay, now you are converting atom into gaseous state right now. So now the minimum amount of energy required to remove an electron from neutral gaseous isolated atom. See, if this is an atom having one valency some electrons, but what I am doing, I am supplying some minimum energy to remove one valency electron from it. So that energy, see, whatever the energy we are using, that is called ionization energy. Okay, see, there is an element M, so we are removing one electron from it, it becomes unipositive. If this is an atom, I am removing one electron, so that it becomes A plus, that one electron is removed out. See, removing means I am using some energy on it now, so it means I am supplying some energy to the system, so it is called endothermic reaction or endothermic process. So ionization energy is always endothermic process. So it is indicated with delta H positive. So it means it is an endothermic process. Okay. So one electron we remove now. So this is first ionization energy. Okay. See, array. Inside nucleus is there, outside electrons are there. We are removing electron from outside, but inside what they do? That nucleus will drag the electrons. Right now. So if more is a positive charge, more strongly bind that valence electrons, yes or no? But from outside I am trying to remove it. Is it easy or difficult? See, now removal of one more electron from here. I am making it A plus 2 and removing one electron. Tell me, I am saying this is second ionization energy. Okay. So tell me which is difficult, removing electron from atom or from here? From A plus. It means always second ionization energy will be greater than
first ionization energy
for an element. Okay. So if I compare successive ionization energies, the last one will be highest one compare with the first one. So like this. So IE1, IE2 if I compare, IE4 will be greater than 3, 2, 1 like that I am saying. Is this clear everyone? Yes. Next. See, if this is the nucleus, here electron cloud is there. Okay. Again. If this is the nucleus, here electron cloud is there, valence electron cloud you consider. See, which electrons are very close in the first case or second case? It means if it is close to the nucleus means removal of electron easy or difficult? So it means down the group size increases now. What happens to ionization energy? Decreases or increases? Decreases or increases? Decreases. So down the group size increases now, that valence electrons will far from the nucleus. So it is easy to remove out. So ionization energy down the group decreases, you can remember. Okay. Now from going from left to right, what happens to ionization energy? They will say increases. Why it is increases? They will ask. Because that electron is entering into the same shell, so it is difficult to remove the electron. So you can write like variation in ionization energy across the period down the group. Okay. So in a group, top to bottom ionization energy decreases. In a period left to right ionization energy increases. So for this ionization energy increases, I am saying now. You put one star mark for this. It means there is some exceptional things to be studied here. Not exceptional, that is conceptual concept to be understood. It means what we need to know is generalized statement is left to right ionization energy is increasing, we are saying. But there are some factors deciding exactly how ionization energy changes. Okay. Now see, if more positive charge is there inside, is it easy to remove the electron or difficult? So ionization energy directly proportional to nuclear charge. Okay. Next, ionization energy, what about size? Small size difficult to remove. So ionization energy inversely proportional to size. Next. What about electronic configuration? Third factor is electronic configuration. So when it comes to electronic configuration, see, second period elements first. Tell me, what are the elements we have? Lithium. Please try to listen to this very carefully, because from here we can expect. Okay. So it's electronic configuration, you tell me. Next. Fine. Okay. And the next one is neon. Yes, to. See what I told you, when their electronic configuration is either half filled or full filled, it is stable. If a system is already stable, I am removing one electron from it. Is it easy? No, it is difficult now. So whenever there is stable electronic configuration, removal of electron is highly difficult. So it has highest ionization energy. So in a period, which element will be having highest ionization energy? Noble gases will be having highest. Okay, right now, because they have half fully filled electronic configuration. So in any period, noble gases will be having highest. Keep it aside. Next one, here it has a p5 electronic configuration, and we know fluorine is highest electronegative element. See, electronegative element, what it will do? It will try to gain the electron, but it won't try to give the electron. So that's why next one is fluorine. Now comes here oxygen, nitrogen. See, nitrogen half filled electronic configuration now. If I remove one electron, what it becomes? It becomes like 2s2, 2p2. See, a stable configuration becoming unstable. So will it give that electron? No. So due to this reason, nitrogen have more ionization energy than oxygen. So what you should write here? The next oxygen. Next carbon as it is. Okay. After writing boron and beryllium, see here it has 2s2, here it is. See, this one electron easy to remove, then this fully filled electrons right now. So that's why beryllium, boron. And one more concept here is, if this is the nucleus, how this s orbital lies? What is the shape of s orbital? Like spherical, we'll say. But p orbital means dumbbell you are saying. See, around the nucleus, you just imagine you are inserting s orbital. See, from all sides that nuclear forces are equal, so strongly hold that s orbital. But when it comes to p orbital, this is not symmetric all round right now. So force is not symmetric. It means which is close to the nucleus, s orbital or p orbital? S orbital. So it means if electrons are lying in s orbital, that will be having greater ionization energy than the p orbital. It means that s orbital is more close to the nucleus. That closeness to the nucleus is called penetrating capacity. What is that? Penetrating capacity. So the penetrating capacity of s orbital is greater than p, greater than d, greater than f. So more is the penetrating capacity, more is the ionization energy. So that's why beryllium is coming first. Next one is boron, and least is lithium. Now you got this now? So write this. Along with this, you tell me same, this is second period elements. Now tell me respect to third period elements. Lithium, down to it, sodium. Next, enough. Tell me for this. What is the order? Phosphorus. Next. This one. This one. Okay, remember this. Done up to here? No. You can write later. Okay, answer me this fast. Okay, Ram. See here, one last example. We'll extend the class, no issues. Okay. See, what is the electronic configuration? See, there is an element like carbon is an element, I am saying. What is its like electronic configuration, you tell me? 2p2. See, here, what is the valence electronic configuration? 4. This one. So inside this 1s2 electrons are there, they won't participate in chemical reaction. So they remains inside only. Okay, will they come out? No. So I am just in. Okay. What we are discussing? Yeah. So this many valency how many valency electrons are there? 4. So this 4 can participate, but this inside no. So we can easily, we can relatively remove these electrons, 4 possible electrons, but removal of this inner electron is highly impossible or highly difficult. It is possible, but more energy is required right now. So whenever there is a very stable electronic configuration, we cannot remove the electron. Now if you see this, from here to here energy is increased. We know successive ionization energies increases. See, read this question, successive ionization energy is given like this. What will be the element they are saying? See, from here to here it is increased, from here to here also increased. But if you observe, from here to here it might be around 3 times, from here to here not even 1 time also, but from here to here almost some 8-9 times. Are you seeing? It means there is a very drastic increment in the ionization energy. It means the third electron, up to 3 electrons you can easily remove electrons. But after 3 you got a very stable electronic configuration, but it means from here we cannot remove. So which element will be having that 3 electrons loosely bonded and the next electron should be strong? It means inside. It means the element that has valency electrons as 3 will be your answer. Now boron electronic configuration, you tell me. 1s2, 2s2, 2p1. For this one, 2s2, 2p2. This one, 2s2, 2p3. So now tell me which is highly difficult? Highly difficult for first one itself. But they are saying first 3 are easily you can remove, but fourth one is difficult. Boron. See, up to here you can easily remove. After that you got a helium gas configuration that you cannot remove. So that's why it required highest. So which element it is? Boron. If I ask for carbon, how it should be? After removing these 4 electrons, this kind of very big increment in the energy will be observed. Okay, like that you need to identify. Okay, then the remaining things we'll discuss in the next class. So you just go with the things that we have discussed and you can solve the questions also. Okay. Right. Slides. What?